Okay, welcome to the last session of today. My name is Antti Tölli, a professor at the University of Oulu. I'll be chairing this session titled as RIS, sub-THz and D-MIMO. Will those make 6G visions a reality? Well, I'm not sure whether we will hear a definite answer to this question, but I'm expecting at least to see a lot of equations. So please do not disappoint me. So we have 4 talks, each focusing on one of the current hot topics of physical layer processing considered in beyond 5G research. The first one is related to reconfigurable intelligent surfaces. Second one, integrated sensing and communications. Third one, extremely large MIMO arrays with low precision processing. And finally, we have a talk about distributed MIMO. So we will be shortly learning about some recent advancements of all these 4 topics. So let's start with the first talk. It will be given by Professor Markku di Renzo from Centrale Supélec and titled as Flexible Intelligent Meta Surfaces, Multiport Network Modeling and Optimization. Please, the floor is yours.
Thank you very much. Thank you very much for the introduction. So very happy to be here. Thank you very much for joining this this session. So as basically was said, today I will be talking about RIS. I'm not sure if the slides are already on or you can see them. Yeah. Thank you. Thank you very much. Okay, so as I was saying, I will be talking about reconfigurable intelligent surfaces, or maybe something more advanced than that, or at least not the original definition of RIS or RIS. It's something more recent that we call now flexible intelligent metasurfaces, or FIM or FIM for simplicity. And I will try to introduce this concept to you, but of course, first of all, I will recap on what RIS is, what the different options are, and then why we are moving forward to this new technology. So the presentation will be split into parts. Part 1 is a little bit more general, really perspective, broad overview, a lot of figures. The second one will be a little bit more technical, a little bit more mathematical, and is part of the second, the subtitle, if you want. So this multiport modeling and optimization, which is somehow a way to bridge the communication theory and electromagnetics for analyzing these surfaces. So let's recap what this programmable or intelligent for communication people metasurfaces are. So we are looking at these structures, at least conceptually. So we have basically these tiny antenna elements in red, which are passive, just scattering elements. And then we have some electronic circuits, which allows us to change the response of this structure over time. From an ideal point of view, each of these elements, the antenna plus the electronic circuits, usually are modeled in terms of scattering coefficient. It can be reflecting, it can be refracting, we will see. But essentially, an input, a signal that illuminates the structure. Each element applies an amplitude and a phase shift, which can be independent from the others, or they can be coupled, as we will see. And at the end, we get for every element an output, and we try to optimize this coefficient, capital theta, to obtain some results, okay? To focus the energy somewhere, for example. So if you want to know more on what you can do with these intelligent surfaces, this is a paper that was recently accepted in the proceedings of the IEEE with many of the people who have contributed to this year, as you can see from the long list of authors. And the first part is based on this paper. Okay? So these surfaces have been utilized in wireless communications for many purposes. The first one has been this one, so somehow implement the relay functionality at a lower complexity and lower cost. So we call this relay type. The idea is that you take the signal here and then you try to reflect somewhere, so to steer the direction of reflections or the direction of refraction. With respect to conventional relays, we would like to reduce the power consumption and the complexity and also the latency, if you want. Then, I mean, these surfaces have been utilized also as a transmitter type. So the idea is that imagine that you have a backscattering system. So you have this surface, but you have sensors, and you want to backscatter this data that you sensed, a temperature, for example. You may encode this data onto some activation pattern of this surface. So you encode it onto the unit cells that are on and off, and depending on the bits that you want to transmit. And you can try to decode this at the receiver. This is another nearly passive implementation. Now, I mean, there are many people who are utilizing these surfaces not only for reflection type or refraction type operations, but also as a base station antennas. So you can actually coat your antenna with these surfaces. And then when the signal radiates from each element, you get a rich scattering environment. So you can create a rich scattering environment and then to take advantage through your MIMO base stations and spatial multiplexing, etc. For some people who have been working in the field of spatial modulation, this reminds a lot the concept of media-based modulation in the past that was proposed quite some years ago. Okay. Now, I mean, the typical architecture that we have been looking at is primarily the one that we called nearly passive metamaterials or metasurfaces, because essentially we don't want to have any sort of power amplification. So the only power that we need is for the electronic circuits. So we need to have some power, so it's not completely passive, okay, but not that much compared to other technologies. But this has some pros and cons. The pros is that we consume much less power, but the range, I mean, the distance that we can reach is relatively limited unless this surface is sufficiently large. It needs to be massively large in order to go very, very, very far. So some people have been looking at other solutions, some hybrid, in which some of the elements might be active. So you may have a phase shifter plus some power amplification, or also a tunnel diode. You will find the references in the paper where basically this has been also implemented. So there is a trade-off, a bit more complexity, a bit more power consumption, but your range can be longer. And also you can simplify your channel estimation because you have active elements, so you can start sending pilots and receiving pilots, so it's a bit easier. Okay. And then there have been some recent advantages, recent developments where you don't want only to, for example, reflect the signal from a wall here, but also to transmit the signal, so to refract and to have this joint functionality, reflection and transmission. The reason is if you deploy this surface somewhere, only 50% of the users, so those who are in the reflection region, can benefit from it. With this structure, all of them can benefit, all the users in the network can benefit from this surface. And it's also called the omni surface for these reasons, or simultaneously transmitting and reflecting surface. Okay. Once again, the complexity increases, and so there have been many proposals. The most complex one, where each element can do reflection and refraction at the same time. You may have some elements that can only do reflection and others that can only do refraction, or you can have elements that switch between these two functionalities. Okay, these are all solutions that have been very much studied in the literature. More or less, they share the same pros and cons. Okay, and then the last one that I'm telling you today is utilizing these surfaces for building truly massive MIMO antennas that we called holographic MIMO, where essentially you have your feeders coplanar to this structure, to this metamaterial surface. They create a surface currents that can be arbitrary in distribution, and then this radiates and reaches the destination. You can enhance this even further if you have this multi-layer or stacked structure where you have multiple layers. And through these multiple layers, you can do more advanced signal processing functionalities. And I discussed a few days ago in a workshop that was co-located with this event. So I guess this is what we will find in the literature. More or less, I mean, you will find a little bit more, but these are the most important structures, according to my understanding. So what's next? Next, from what I understand, is that these structures, they share one fundamental, two fundamental components. The first thing is that they are planar structures. So we are always talking about structures that are planar that we deploy on the wall. But there are many surfaces in the environment where they are not planar. So you can see this example here. And you can see also, I mean, these kind of structures where you may want to have surfaces that are conformal. Okay, for example, a cylindrical shape. For your information, there are now quite a few papers for vehicular applications discussing this kind of structure. So we would like to go from planar to conformal. So to try not to avoid the cases that we studied. And the most interesting one, which is a sort of generalization of this conformal, is what is called metamorphic metasurfaces, or in the field of antennas, movable antennas, as I will tell you now. What is the idea? The idea is that in conventional metasurfaces or programmable metasurfaces, the antenna structure is fixed. These red elements are fixed, and we optimize the electronic circuits. Here, the idea is that we can also optimize the position of the scattering elements in space. So we have a sort of dynamic range or morphic range that we can tune, and we can move basically the position of the elements to have extra degrees of freedom. The functionality is always the same. You want to do multi-user MIMO, reflection, transmission, etc. But the idea is to have this surface that is that can change basically shape if you want. Somebody called this one student that I'm working with called it the dancing metasurface to give you an idea of what this is going to do. And we call this flexible intelligent metasurface, where the flexibility is on the shape. So this is motivated by recent advances in the field of metamaterials. There are a lot of works, I mean, on building metamaterials with these structures. Also, I mean, recently, of course, I mean, you need to pay a lot of attention on the elasticity of the material on the substrate. But I mean, there are quite a few experiments and prototypes, especially in China and in the US, working basically at implementing that. And this is an example from a paper that maybe does not belong to our community. It's an ACM paper, which actually was published quite a few years ago now. It's a 2020, 2021. It's one of those very highly selective workshops in the computer science community, where you can see, for example, that you could put motorized curtains. So you have this, antennas put on the curtain, and then this moves, can be opened, closed, and then basically you can get that. Don't have anymore a flat surface, or you have something like that. Okay, so these are two examples that are maybe more for academic trial. I mean, to understand what is happening, but I mean, this gives you an idea of what people are considering. So, in the field of antenna design, there is also quite a lot of interest in this concept of movable antennas, which is very much closely related to what I'm telling you, even though the technology is slightly different. So the idea is that you may have an antenna where you have multiple ports, and then you can connect your RF chains to these ports, okay? Or you can basically move the locations of the actually on the antennas if you want on the structure. Why you do that? Because you could optimize the location of antennas in order to compensate for the fast fading of the channel. So even at a very small wavelength, you can have a very deep fade, so you can move your antenna and try to compensate for the deep fade. And there are now quite a few research works on these movable antennas in the literature. Or Kai-Kit Wong from UCL call it fluid antennas. The concept is essentially the same. Okay. So this is the kind of introduction part, in the sense the most general part of this presentation, or maybe the less technical. So what I wanted to convey is that there have been quite a lot of work in the field of reconfigurable intelligent surfaces in RIS. But now, I mean, people are really moving forward, considering much more advanced structures. And for this, there is not really much of research, all in terms of modeling, in terms of optimization, etc. So today, I'm going to show you some recent results that we obtained, in the sense that the papers were put on archive less than 1 week ago. So it's very new. I never presented. This is the first time that I presented these results. Okay. So I will focus on modeling and optimization. Modeling, because I want to do the modeling in a more accurate manner than I told you. So the original example that I presented, this ideal phase shifter, forget it. Okay, that's good only on papers, but will never work in practice. So I will show you a better modeling approach that we validated also with the full web simulations, and then how moving from this better modeling, we can do some optimization in order to optimize the locations of the scattering elements and the electronic circuits. So if you are interested in all the details, which I will not be able to describe today, you can have a look at these two papers. So this first paper is a joint work with colleagues in Singapore and some other fellows, Binspoor and Layo Sanz and Merwan Deba. And the second one is a collaboration with NEC in Germany. The first paper utilizes a model that is conventional for communication, so this phase shift model, ideal phase shift model. The second one utilizes a model that is much more electromagnetically consistent. And today I will be focusing on the second model, on the second paper, and to show you both the modeling and the optimization part. So let's start with the with the modeling. So I will try also to tell you what the limitations are in current modeling. So the idea is that we would like to have a model for the structures that bridge a little bit the gap that there is accuracy in electromagnetics. So if you open any papers on transactional antennas and propagations or metamaterials, the models are pretty complex, and it's very hard for people like me, a communication person, to deal with them, and the very simplistic models that I showed you before. So the idea is that we have a transmitter, we have a bunch of receivers, so one receiver, and we have a complex environment, and we deploy these surfaces. It can be an RIS, it can be an FIM, it can be an SIM, stacked intelligent meta surfaces, whatever. The technique applies in any case. What we would like to have is to have a model that allows us to link the signals that we have at the receiver as a function of the signals that we have at the transmitter. And then we have a channel here, a sort of MIMO channel. So this resembles a lot the usual MIMO signal model. So Y is equal to H multiplied by X. So that's the reason it's useful for us. Let's start with the free space, which is the starting point to understand the thing. So there is no scatterers, there is only the RIS, the FIM in the environment. The approach that we utilize is based on multiport network theory. So what is fundamentally, what do? We represent this system as an equivalent circuit. Okay, and every antenna in this system is modeled as one port on this multiport system. So this is the antenna, the transmitter is one port of the system where the signal is emitted by a generator and goes to the system. At the receiver, we have the same. A port is basically an antenna connected to there. And then we have the model for the FIM or RIS that is basically, again, another port. Now, to visualize a little bit better, we may think of this. Okay, this can be for an RIS, FIM, whatever you want is exactly the same. So here I utilized as a unit cells some dipoles just for ease of representation, and also because mathematically speaking, we can write the equations. The technique can be applied to whatever the antenna type is, but if it's dipole, you can write down in the math. If it's not a dipole, you need to feed this model with electromagnetic simulations. Okay, but the model itself is correct. So we have dipoles at the transmitter connected to generators, dipoles at the receiver connected to impedances that are the circuits connected to there. And then we have these structures, this programmable metamaterial that is modeled as tiny dipoles connected to impedances. And the idea is to compute this end-to-end impulse response, impulse response that we can get by utilizing this theory. So now dipoles, I told you, they are utilized for simplicity, but also because there are papers in the field of metamaterials and applied optics that tells us that complex metamaterials might be approximated by using a bunch of dipoles connected to impedances. That's one of the references. I will show you another reference in a while. So on the one end, it's simple mathematically. On the other end, we may be able to approximate more complex structures as well. Okay, so I'm not going to bother you with the proof, but at the end of the day, if you use this structure, so if you write all the equations and then you express the voltage of the receiver as a function of the voltage of the transmitter, and I will show you some steps, you get this end-to-end transfer function. So this is relatively a bit ugly if you look at it from like this, but it's extremely intuitive and simple at the end of the day. Why? Because there are terms in this big equation. There are two main matrices that we need to focus on. The one in blue is the matrix that accounts for the essentially for the interactions between these two elements. So we don't model anymore an RIS as an ideal reflecting elements, but we take into account the mutual coupling between the elements. And this is everything in this matrix. Then I will tell you how to compute the entries of this matrix. But for the moment, this from a system level point of view, this is the matrix that tell us the interactions between the elements, also the mutual coupling. And then there is this matrix, which is nothing else than the impedance is connected to the antenna, to the dipoles, which means the variables that we can optimize. Some of the variables that we can optimize, okay? So at the end of the day, we can clearly see that there is the impact of mutual coupling and the impact of the variables that we can optimize. It's clear where actually it is in the system model, okay? Now, this is for a very simple system model because it's free space. You may tell me, okay, but it's already sufficiently complicated. If I consider a realistic channel model, this will never work. But indeed, this model is scalable. And even if you have a multipath like this, so you have a clustering objects, you can model each cluster as a multiport network. Essentially, there are papers that have shown that if you take a material, an arbitrary material or metamaterial, you can approximate again this material with a bunch of dipoles, with some characteristics, length, for example, and with some impedances connected to the dipole themselves. These impedances now are not reconfigurable; they are fixed, and they depend on the material properties of this structure. Okay, and here, for example, you have a paper that has shown, from the mathematical point of view, this modeling approach. Once you can model every scatterer as a multiport dipole, then you can easily generalize the model that I showed you before. And indeed, at the end of the day, by doing the math, you get this formula where you have, again, the end-to-end channel, where you retrieve, again, the two matrices that I told you before, which I've already explained to you, but plus you have other terms that takes into account the scatterers. Okay, so the structure of the model doesn't change, it's sufficiently general, and can be also utilized to do some optimization, as I will tell you in just the few minutes that are left. Okay, so what I would like to tell you is that we have now a model that is okay. We have now a model that is sufficiently, let's say, general to be utilized for signal processing and not bad from the accuracy point of view, from the electromagnetic point of view. Okay. Out of curiosity, I mean, the terms of these matrices can be computed in this way. So they depend on the electric field generated by this guy observed here, projected on the current that flows here. So they can be analytically computed for dipoles. For general structures, they cannot be computed. You need to do the simulations. But the model itself works. You just need to compute the entries through full wave simulations. Okay, so now that we have the model, we would like to see whether we can utilize it for optimization. And essentially, we would like to see what do we gain from moving from an RIS to a flexible intelligent surface. That's what I would like to show you in the next part. To show you the gain, I need to show you how we can optimize this model, which accounts also for the mutual coupling. This mutual coupling model applies also if the elements move, okay? It's completely general. So the approach that we developed is the following. So first of all, we compute the channel model as I told you, and then we optimize two variables. We optimize the impedances connected to the RIS, so the configuration of the RIS, and also the position of the element. Oh, let me tell you that if you change the position of the element, then these elements change. So this becomes a variable of optimization, because this is position dependent. Okay, which means that in conventional RIS, this is your variable of optimization, and this is fixed. In flexible metasurfaces, this is an optimization variable as well. So you have two optimization variables that you need to optimize, two matrices, and not only one matrix, with different feasibility regions. Okay. So we did that. Now I don't have much time. I need to close, but I just want to give you the idea of what we did, and then I show you the results quickly. So we formulated a problem which is really maximize the received SNR the SNR at the receiver with the model that I told you. The optimization variable is B, which is the status of the basically the circuits that is connected to the RIS. Okay, and Q, which is basically the locations in a 3D space of each element of this RIS. So we have two optimization variables: the state of the circuits and the locations of the unit cells, which belongs to two different sets. Okay. So the approach is not super optimal. I mean, it was the first paper, so we utilized optimization tools that are known. We utilize the alternating optimization, which is we optimize the configuration of the RIS, and then we optimize the locations of the unit cells, and then we keep iterating until we reach convergence. Okay. So if you are an optimization person and you want to know the details, the optimization of problem number 2, which is the optimization of the RIS, can be found in this paper, which is pretty general. And what we did, we utilized this trick. So if you have n elements to optimize, we fix n minus 1, and we optimize one at a time, and then iterate. And the big problem here, from a mathematical point of view, was this -1 inversion, because the channel is non-linear because of this matrix inversion. And we utilized these 3 steps. So we had first to rewrite this -1 by utilizing these 3 steps. And then we linearized the system, and we managed basically to solve the problem. If you are working in optimization and you want to know details. So the solution is suboptimal. So we converge to a local optimum, so a stationary point. And the problem 3, we used the 2 steps. So what we did, we used the gradient ascent method and projected on the feasible space, which can be rewritten like that. And then what we utilized in order to linearize the problem and to avoid this to the power of -1, we utilized the Neumann series approximation, which we introduced also some time ago to solve similar problems. Provided that this is fulfilled. So I'm not going to go much into the details because I need to stop. But if there are people interested in optimization, we can discuss in the Q&A or later on. I mean, at the end of the session. So now let me show you the results. And the aim of these results is to show you what do we gain moving from a fixed structure to a movable structure, so a flexible structure. Okay, we already know what the gains are or reconfigurability. We just now need to look at what we gain if we change the locations of the tiny antennas. In gray here, you have the typical configuration for a linear antenna structures. And then we optimize the locations. And you can see that the optimal locations in the considered setup, which is 1 transmitter and 1 receiver at some locations, is this one. You can see that it's pretty different, but you can see that the gain is quite significant. So you go from here, which is 33 maybe, to 39, something like that, dB of SNR, okay? With a planar antenna array, you also have quite significant gains, okay? And then you can keep going with the cylindrical structure, where you can actually optimize the locations of the antennas, assuming that you can move the antennas along the substrate, and the same for the spherical surface. Okay, these are structures that were chosen by our collaborators at NEC based on some of the applications that they are looking at. But the bottom line is that there are a few dB in terms of gains that you may have if you add also the extra degrees of freedom of the location of the element, thanks to the flexibility that this meta surfaces gives to you. So besides the paper that I that I showed you, I would like also to close and steer you towards this other paper, which is on next generation advanced transceivers, where you will find not only intelligent surfaces, but you will find something something more, which goes from MIMO, reconfigurable intelligent surfaces, flexible surfaces, and also semantic communications and the role of machine learning. So this is the opening paper of a special issue in JSAC, which has exactly the same name as the paper, okay, which is now the papers are under review. And you can see the collaborators. And with that, I close. So this is just to acknowledge the fact that we have a very large scale project on future networks, which does not involve only physical layer, but many layers. I'm involved mainly in the technology and the fundamental parts of this. So with that, thanks again the organizers for the invitation. And if you have questions, I'm glad to take them. Thanks.
Okay, thank you, Marco. At least we saw the plenty of equations as I requested.
Sorry.
Okay, any questions from the audience?
Very interesting presentation. My question was, did you optimize only the location of the antennas or the elements, or did you optimize at the same time location, amplitudes, and
circuits? Yeah.
Everything at the same
We did
time.
exactly that. Yeah, we optimized at the same time the locations and the circuits. So fundamentally, if we can go back to the slide, yeah, thank you. So fundamentally, maybe here is you can be this point here corresponds to optimizing only the circuits. And then, which is basically the starting point of the optimization on the second optimization. So optimizing circuits and position in an iterative manner. So here you can clearly see the gain of optimizing the positions in addition to optimizing the circuits. Of course, the optimal value of the circuits is different in the two cases. They're not exactly the same values. And this takes into account also the mutual coupling, yeah, which changes if you change the location of the elements.
And this shape here, the green shape, does it change with the statistics of the channel or the instantaneous channel? Or?
Yeah. So this was basically the results here. I think so, at least. So these results are obtained for free space. We limited to the simple case because it was a little bit difficult to get intuition for this paper. But definitely, yes, if you change, for example, or just the location of the receiver, so your channel between the RIS and the receiver changes, the position will be completely different. Also, these results are obtained without putting any constraints on the space on which you can optimize can put the locations. We have also results when you put constraints, so you constrain this morphing range that you can actually have. Regarding your question about the channel, the best paper that you can look at, but the model is simplified, is the conventional model, is the other one, is the one with Zhang Sheng, where there, the first paper to the left, where there you will clearly see basically what we did is the following, the surface, and then we consider different locations of the scatterers, and we showed what happens when you change the location of the scatterers. And there you will clearly see that depending on the number of clusters, the position of the scatterers, the locations changes completely. And also the gain that you may get. Yeah. But the model is simpler. The model, yeah. Okay.
Okay, I have a non-technical question over here.
Okay. Yeah. Sorry. Yeah.
With the classical antenna, there are rules, for example, on where you can place it. Like it has to be a certain distance from schools or hospitals. In the vision of placing these on cars, which are moving, is there any discussion about what the regulation might look like?
Yeah. So that's a very good question. So I don't know if there are actually discussions about that. What I mean, I can say that definitely, I mean, they should be. So the general idea of this surface is in any case, there are two main things. First of all, I mean, these surfaces do not really amplify the signal. I mean, they don't add basically power amplifications. That's the point. The other things that can be done, and we studied that, is that besides the constraints on maximizing your rate, so your capacity, your signal, you may also impose some limitations on the radiations that you need to create on some given area. So you may optimize your system such that you say, I want to maximize the signal inside the car in some spaces, in some subspaces there, but I want to minimize the signal where there is the location of the passengers, for example, or there are other things. That can be done. We studied that in a European project that ended, I mean, last year. It's called the RIS 6G, where especially the telecom operators were very much interested in this kind of thing. So the idea was really to create areas where the electromagnetic radiations was very low. We brought also some papers. That's a very good point. So this multi-objective optimization that accounts for that, especially in an environment like a car, I think it makes a lot of sense. So yes, we didn't study that. Maybe, I mean, also the locations of the tiny antenna elements will change. So that's interesting, yeah. I'm not aware of discussions in terms of regulations and these things. That I'm not aware at the moment, yeah. Thank you.
All right, thank you. Okay, quick question. Okay.
Yeah.
So I'd like to know about the optimization part. In my understanding, so you'd like to optimize the location, and I'd like to know what kind of information do you need to optimizing the things?
Yeah. Okay, I got your point. So fundamentally, the information that you need is the entry basically of these matrices. In order to get the entry of these matrices in a free space channel, what you need to know is the location of the transmitter and the location of the receiver. Then, based on the location of the transmitter and the receiver, you can compute the channel as a function of the location of the points, which is an optimization variable. So you need to know where the users are, essentially, assuming that the base station has a fixed location. If you are in a multipath channel, the thing is more tricky. So we have results that assumes that you know exactly where the scatterers are, and this gives you the upper bound. You will never get this in practice, but you can optimize the second order statistics. So you can optimize the average with respect to the spatial distribution of the channels, and we did also that. So essentially, you need to know either the exact locations of the receivers or the second order statistics, so the spatial covariance matrix, etc., that gives you this. Yeah, that's essentially the idea. Yeah. Thanks for the question. Yeah.
Thank you for the questions. I think we need to move on.
Thank you very much.
Thanks again, Markku. Thanks, Markku. Very interesting talk. Okay, let's move on in the agenda. Our next speaker is my colleague, Professor Markku Juntti from University of Oulu, and he will be giving some insights, recent findings related to ISAC, or Integrated Sensing and Communications in 6G systems. Please go ahead.
Okay, thank you, Antti, and thank you, everyone. Thank you, Markku, for very nice presentation. So the session is about RIS and massive MIMO and such, and I was kind of asked to talk about that, but then I saw, let's say, something about the other presentations and decided to talk about ISAC, which is not about RIS that much in this talk, but definitely we are using large arrays and MIMO is in there. So, and I try to be a little bit general here, not going into too many deep equations. There are some insights on that. Okay, this illustration we of course have seen already. So it's just here to remind that when we move, at least according to the current understanding, from 5G to 6G, from IMT 2020 to IMT 2030, although as we have heard many times during this event as well, the precise requirements are not known, not there yet. Still, we have a vision that there will be evolution of these 3 use cases and then 3 new ones. And out of these 3 new ones, I consider this integrated sensing and communications, which is my focus today, is as one of the most interesting and exciting ones, in the sense that in some sense it's really new. Of course, ubiquitous connectivity was somehow there as a general target already, not saying that we have succeeded and not saying that 6G wouldn't be needed to make it really happen, but ISAC in a larger scale was not yet there in 5G. And what I'm going to talk about today is first some general views. So what are the motivations? What are the use cases? Mikko gave very nice talk about HexaX view. I will take some HexaX points here as well from the ISAC, focusing on the ISAC perspectives. Then I will tell a little bit about our recent technical work on one aspect of ISAC, dual functional radar communications design in the MIMO context, in the spirit of the session, and then a few concluding remarks. So first about these generic use cases. So the current term, which is most widely used in this discussion, it's in the ITU view of the 6G should be. It is in the Atzeni standardization. There is this integrated sensing and communications ISAC industry specification group chaired by Alan Murad, who was talking here yesterday. don't know if Alan is still here, but he's doing great work leading the pre-standardization discussion and efforts in that arena. But there are other terms which are essentially synonyms, like joint communications and sensing. Both refer to the fact that we share some resources, and we try to typically hardware resources, often also spectrum, and we try to use the network and the available infrastructure, frequencies, signals, not only to convey our message in the communications, but also use the system as radar. Then there are, of course, higher layer approaches where we use like network traffic information or application level data to do sensing and inference on different phenomena. And that's part of the ISAC framework, but I'm not going to go into that discussion today, at least not much. So my main focus here is on this radio signal, physical layer close discussion where we consider kind of radar type operation using, for example, the available pilot sequences in the system. And I already mentioned that there is quite a bit interest in the standardization already, or the standardization discussion for this. So 3GPP has identified about 30 possible use cases. Etsy has this industry specification group, and Alan already explained quite well yesterday what are the cases there, so I don't need to go too much into that here. And then few points from this HexaX view and HexaX2 view and discussion. This task is led by Chalmers, Henk Weimers, and Doubly and Hexa has defined some of the terminology. So positioning was already in 5G and is there. There are reference signals to assist positioning. So positioning typically refers that we try to find a position of a device which is connected to the network itself. While then locationing is more general, it can also relate to finding positions of unconnected objects. And that's where we are typically interested in this sensing. We want to sense the presence of some object like pedestrian in some area, position of the robot, which is not connected to the network could be one use case. So like in radar, there are these functionalities that we try to detect that something is there. And once we detect, we try to estimate the position where it is. And then this joint communications and sensing, integrated sensing and communications typically refers to the framework where we jointly design both functionalities and in the best case for mutual benefit. And HexaX2 has defined various use cases, scenarios like we can use also the global positioning services of the or global navigation systems provided by satellites as one ingredient. But for example, in the indoors, they don't typically work that well. And that's the reason why we need something else. And the idea is usually to use the communications infrastructure and the available signals to find out the positions of the users. And we can borrow techniques, of course, from the radar literature and the radar concepts. We can do monostatic sensing so that the same base station typically is listening to the echo from the environment to infer the positions. We can do bistatic sensing so that the neighboring base station is listening the echo of the other base station, which has the benefit that we don't need to deal with this full duplex problem where our own transmission is hiding the weak echo coming from the target. And then we can do MIMO sensing and multistatic sensing so that we have multiple base stations listening the echo. And in principle, we can also do this via uplink sensing as well, so that base station listens the echoes of the uplink transmissions. And And the security and trust is, of course, very important design consideration here, because if the users don't trust that the, let's say, sensed information about their presence or absence or anything is used ethically in an ethically sustainable way, then of course this business and use case will not fly. Okay, so that's somehow the general framework. And then let's say one highlight how we could do it in the MIMO context, and which has been discussed quite a bit in the literature, where we have also recently done some work. So we consider here a downlink monostatic sensing. So we have a base station which is serving multiple users and also trying to sense the presence, absence of objects. And there are different ways to formulate this problem. And one way is that we assume that we have the superposition of radar signal or sensing signal, and then communication signal which serves the users in the cell area. And then we do pre-coding in the MIMO context and try to share the resources and balance the performance of both functionalities. So we can do very communication-centric design so that we focus on, on serving just the users. Then the power level used for sensing the targets can be low and the sensing performance is bad, or vice versa, or then we can balance them in a desired way. And for those of us who are familiar with the MIMO pre-coding research, we can borrow much of the framework from there. So for example, in the multi-user downlink broadcast type channel, we have our desired communication signal, we have the user interference, we have the classical model. Then we can do the designs in many senses like we did in the past. We, for example, could maximize the communications rate or sum rate or minimum rate, all these are there. We have the constraints on the beamformers, power constraint. If we have a hybrid beamformer, we have the analog constraint or the constraint on the fact that some of the antenna elements do only phase shifting. But then what we add there is some sort of sensing constraint. One fundamental way we would like to do it is that we have a constraint on the probability of false alarm or detection, or if we are estimating the position of a target for the estimation accuracy via Kramer-Rao lower bound. That's often quite complex. So a simple way to do it often is that we borrow a desired waveform from the radar literature and wish that our overall waveform, which serves the users and does the sensing, matches to the desired radar waveform as well as we can. And then we can do different optimization approaches for that. Okay, the chair is telling that I need to speed up. So this is the insight. We can do classical optimization with all these schemes. I'm not going through these. I have some references. You can check them from the journals. And then we have also done wideband extension, where we add on top of the previous approach also the use of different subcarriers, either for communications, either for sensing, or jointly both, so that we allocate part of the subcarrier power to sensing direction and part to the user serving direction. And then we can simplify some of the complex optimization algorithms by certain structured machine learning approaches, but not going to go to the details because the time is running. Instead, I wish to go to the conclusions and mention that there are many, let's say, interesting areas of current and future work. So we would like to and are working to extend this over the to do the multistatic sensing or cell-free network or multi-cell network. Then the hardware models here have been quite simple. We didn't really consider in this work yet the channel estimation inaccuracy. We have a recent work which will appear in the IEEE radar conference in May and a journal extension in preparation where we look at that aspect. And in the spirit of the session, it's also of interest to look this RIS as part of the system because that can enhance the beamforming and in some cases enhance the signal to noise ratio and also provide an additional virtual anchor for this positioning or location finding service. And here is just an example of ray tracing-based emulation, which shows that RIS indeed can, in different frequencies in a real outdoor environment, provide quite useful link gains. This is not the ISAC really, but showing that the potential is there. I guess that I didn't exceed my time too badly, so thank you.
All right. Thank you, Markku. So questions from the audience. Meanwhile, you're thinking about questions, I might ask one.
Okay.
Earlier we heard from Miguel this image-aided sensing. So are these two things just a plug and play, or is there room for some joint optimization, things like that?
I think both. I mean, to some extent, I guess you can just plug and play. You do one sensing with these schemes, another with those, and then try to match them. But I'm sure that you can also optimize. And for example, this channel-aware sensing, like Miguel was saying, if you have an image of the environment, I think we can already get good prior information of the locations of the targets and use, for example, Bayesian setup to improve our accuracy. So I'm sure that there is room for interesting joint optimization.
I think that's the way.
I agree.
Hello, Markku. I am Giovanni from IMEC.
Okay, hi.
Thank you very much for this talk.
Thanks.
I ask you just as estimation. So let's say there is hardware for communication. We do research moving from a perspective of hardware from communication or hardware for radar to hardware for joint communication and radar. At least as preliminary expectation, what would you expect is the challenge? Or I mean, let me rephrase. If I give you hardware and you say, Giovanni, this is for communication, I need actually this feature or this for radar, what would you say? Let's say high level expectation. Thank you.
Okay, that's also a very interesting question. Yeah, I must say that I didn't think it exactly from that angle very carefully, but there are many similarities. So both of these approaches wish to do beamforming, either MIMO beamforming with amplitude control or phase arrays. So there is a lot of similarity, and that's of course the motivation. And from that angle, I think that the hardware is reusable with some reasonable modifications. But yeah, how far you can go with simple hardware? There are some trials which use Wi-Fi, very, very basic Wi-Fi to do some very, let's say, very elementary harsh sensing, and it works. So at least you can get somewhere with the state-of-the-art hardware. I'm sure that Juntti could give a better answer because he's working on something like that, but maybe we don't go to that because our bus is leaving, so.
Okay, any other question from the audience? If not, let's thank the speaker, Markku, again. Thank you. Okay, next speaker is also my colleague from the University of Oulu, Professor Italo Atzeni. And he will give a presentation about large-scale MIMO, where the ADC DAC implementation is severely constrained down to 1 bit per INQ at both ends. per antenna. Okay, please go ahead.
Okay, thank you for the introduction and for the invitation to the organizers and to all of you who are still here despite this being the very last session. So given the limited time for the presentation and the time of the day, I decided to focus on only one specific subject. And I would like to present an idea that would hopefully be useful to enable terahertz communication from the physical layer point of view. Sub-terahertz communication, I should say. Terahertz will come later. So, as you all know, we are striving to find large bandwidths to increase data rates. And, well, we are actually hoping to explore sub-terahertz frequencies from 100 gigahertz to 300 gigahertz, and maybe one day even go beyond to the terahertz band, so 300 gigahertz and above. So this introduces several opportunities and challenges. The first of which is that if you go high in the operating frequencies, to achieve large bandwidth, you need to increase the antenna array size. So you need to use MIMO technologies with very large number of antennas to compensate for the path loss and penetration loss. So if you have at the same time high frequencies and large antennas, of course, you have a power consumption problem and complexity problem. So we go from band limited communications to power limited communications. Now the problem is we have a lot of bandwidth, we have to limit the complexity and the power consumption. So we need radical simplifications in the RF architecture. So a concept that I've not heard of during this symposium yet, and I'm a bit surprised, maybe a bit disappointed, is low resolution massive MIMO. What is low resolution massive MIMO? You might have heard, for example, this kind of architecture where we have a fully digital MIMO architecture with low resolution data converters. Digital to analog converters, analog to digital converters. So why would we go, why would we decide to reduce the resolution of DACs and ADCs? Well, because they are responsible for a big chunk of power consumption in MIMO architectures. So actually the power consumption increases or scales exponentially with the number of resolution bits, especially in the ADCs. So you want to limit this power consumption. Also, there are some advantages. For example, if you have, well, the very limit case is when you have 1-bit data converters. So whatever comes into your converters is, in this case, the digital signal is converted into a +1 -1 or a +j to -j in the Q component. So whatever signal comes out of this is a very harshly quantized signal, which is basically a QPSK signal that comes out of here. Okay? There's also another advantage from the hardware point of view is that using 1-bit DACs will allow you to actually relax the constraints on the power amplifier. They're no longer restricted to operate on the linear region. We know from our hardware colleagues that that's a big problem. Same thing on the ADCs. If you use 1-bit ADCs, your analog signal, whatever comes in here, continuous signal, will be converted into a QPSK signal, +, -1, +, -j. That's very harsh. But the power consumption is minimal, the complexity is minimal, and also you can relax, for example, the requirements on the AGCs, because whatever comes here doesn't really matter, it's just plus or minus, all right? So in this presentation, I would like to combine these two concepts and hopefully convince you that this could be a nice enabler for high frequency communications. So we call this doubly 1-bit quantized massive MIMO. What is a doubly 1-bit quantized massive MIMO? You have a massive MIMO array at the transmitter, one massive MIMO array at the receiver. The transmitter array adopts 1-bit DAC, so whatever comes out of here from each antenna is a 1-bit quantized signal, QPSK signal from each antenna. Whatever is received after the channel is again quantized with 1-bit ADCs. So whatever comes in to each RF chain at the receiver is a QPSK signal per antenna. Of course, I should say perhaps that maybe you're a bit scared, but the massive MIMO regime actually nicely compensates for the quantization distortion. That's the whole point. The large number of antenna will help you to compensate for this harsh quantization. So as far as we know, these systems have not been studied in the past. Usually you see massive MIMO with low resolution or 1-bit data converters, either the transmitter or the receiver, which is basically always the base station. In this case, we want to have this extreme case. So indeed, combining 1-bit DACs and ADCs leads to a fully digital system with minimum RF complexity, cost, and power consumption, at least from the point of view of the data conversion. And also, of course, I will anticipate that this will require a truly massive number of antennas, both at the transmitter and receiver. But luckily, when you go to high frequencies, at least in terms of space, you're not very much constrained. You can have like physically compact arrays with lots of antennas inside. And I would like to point you to this reference. Actually, this presentation is based on this recent work with my colleague Antti, Professor Nguyen and Swinderhurst from the US, and it's recently been published in Asilomar conference last year. So what we have here, this is all you need to know. The rest is boring details. So here you have a transmitter where a symbol is first pre-coded and then quantized at the 1-bit DACs. Okay, so you first do some pre-coding of your symbol, data symbol vector. Then you quantize, you transmit over the channel after applying some transmit power, of course. What is received at the receiver after the channel is the signal at the input of the ADCs, which is still a continuous signal, continuous analog signal, which is then again quantized with 1-bit ADCs. And then by applying some linear combining, we aim to recover the soft estimated symbol that we will then map to one of the symbols that were initially transmitted. So this is all you need to understand. The rest is boring mathematical details. Well, not so much, because otherwise I would not present them. But so these are the definitions that I already explained to you. And the only thing that you need to know here is that we try to find some kind of tractable expression for this MSE. So this MSE is the MSE of the transmit signal minus the soft estimated signal, which goes again through a pre-coding, 1-bit DACs, channel, noise, 1-bit ADCs, and then linear combining. So I'd like you to present maybe something interesting that you may want to use in your research. This is a general concept that is quite nice to know, I think. So maybe good to learn. It's called the Baskan decomposition. So the Baskan decomposition basically allows you to write any nonlinear function as a linear function. And if your initial signal, input signal, satisfies some properties, then you also have some properties of this linear function. So any nonlinear function of this input B, we can rewrite it as a scaled version of the original input signal plus a distortion. Well, this is, of course, quite obvious. The fact is that, okay, how do you compute the scaling and what are the properties of this distortion? Well, the scaling can be computed as an MSE matrix. So to minimize basically the MSE basically you can write C as the MSE of B, okay, so given B, okay? And it turns out that if your input signal is Gaussian, you have that this is a diagonal matrix, and in some cases you can find a closed form expression for this. So your ugly nonlinear function sometimes can be treated as a linear function, And I should mention also that this distortion in this case is also uncorrelated with this. So maybe you don't know the distribution of this, but given the fact that it's uncorrelated, it gives you some advantages when you want to compute some performance metrics. And this is what we will do right now. So we will basically, now you have all the tools to understand what I'm going to talk about. I'm just going to apply, as you can guess, this Baskan decomposition. I'm going to apply it here because this is a nonlinear function of an input, okay? And again, this is a nonlinear function of an input, one-bit quantization function, highly nonlinear. So we want to simplify this to analyze them. So in this case, if we assume S is a Gaussian symbol vector, then we have all the nice properties that we want. Whatever comes in here is a Gaussian signal. We can not only write the Baskan decomposition and find all the things in like the linearization of the signal, but we can also find closed form expression for the related quantities. So this is not just an expectation, this is actually a closed form expression. So easy to analyze. Now we're going to do the same here. However, there's a little problem, is that whatever comes out of here is no longer a Gaussian signal. It's a QPSK signal again. So it goes through the channel, yes, with some noise, but it's not truly Gaussian when it comes in here. But we will still apply the same trick. So write this as using this Baskan composition. So the output signal is a scale version of the input signal plus some distortion, which is uncorrelated. But now we don't have a closed form, so we're a bit of a trouble. Yes, but not so much, because actually we're talking about massive MIMO. Most of you know that when we're talking about massive MIMO, we can apply the law of large numbers. So basically, this Y, which is given by this T, which is highly nonlinear, but multiplied by very fat matrix, actually gives you a almost Gaussian signal. Therefore, you can apply some approximations which are quite reliable, and I'm not going through the mathematical details because they're exactly the same as in the previous case. So now we combine all this and we get an approximation of this MSE, again, MSE between the input signal and the soft estimated signal after linear combining. And well, this is quite easy expression, not even any inverse, so absolutely simple. You can do some very basic optimization to optimize the RIS combining for a given transmit strategy. So enough with expressions. Now some figures. So first of all, I'm going to tell you that I think this system model is very promising. However, it needs truly massive antenna arrays at both transmitter and receiver. So this will be some headache for our RF colleagues, but that's not my problem. So we can see that MSE can go as low as 5%, almost 5%, when you have about 40 times 40 planar array in both transmitter and receiver. And here we also compare with the case where we only have 1-bit ADC. So full resolution transmitter, 1-bit ADCs. And the difference is it's quite small, actually. That's quite surprising. So actually what you gain here is a massive reduction in the complexity at the transmitter for a very small gap in terms of MSE. So actually this system is actually quite promising. I'll skip this figure because it's very similar, just saying that how this changes with number of antennas. Maybe I could focus 30 seconds on this one. So here we change the number of streams and check this MSE again. And the number of streams goes from very low to very high. And actually there is a minimum here. Why is that? Because quantized systems, 1-bit quantized systems are actually affected by this effect. On this case, you have this, let's say, noise limited performance because we have very few streams. Okay, and here you have quantization limited. Too many streams will introduce actually some user interference or interstream interference, I should say. And in between, we have this nice trade-off. But so far, I've used Gaussian symbols because they actually apply to our analysis. But what if you use practical constellations? Well, this is what happens. Here, these black dots are the soft estimated symbols around a 16 PSK transmit constellation. Can say that, okay, if the number of antennas is not too large, it works all right, but not so well. But if you go to high number of antennas, it works remarkably well, and you can obtain symbol error rates in the order of 10 to the minus 4, which is quite remarkable. And the difference, of course, with there is some difference with the case of 1-bit ADCs, but not too much. So these systems actually hopefully have some promises. And now, of course, I've hopefully convinced you that this system model can be promising for high frequency communications. However, there's a lot of work to do because here I have assumed many things. Perfect channel estimation. Well, we haven't done any beamforming design, so there's a lot of room for optimizing and analysis as well. So despite the take-home message is that despite its simplicity, doubly 1-bit quantized systems, massive MIMO systems with very large antenna arrays can deliver impressive performance in terms of MSC and SCR, which is not far from that of a massive MIMO with only 1-bit ADCs and full resolution transmitters. With this, I'd like to conclude and just little acknowledgement to projects from Research Council of Finland and European Union. You have heard all day and all week about 6G flagship and XIX among those. So thanks a lot for your attention and happy to take some questions.
Yeah. Thank you, Italo. All right, let's have some quick questions, please.
Thanks for that. Couple of questions. One is that I guess another hidden assumption is this cannot be an OFDM system. It's a single carrier system.
Yes, here.
Okay. Then the second question is, what does your transmit nonlinearity do to your spectrum?
Two very good questions. So the first one, this is indeed a single carrier system. There are some other studies, not here, that also analyze OFDM. The behavior is quite similar. So in that, I'm quite confident. What does, in terms of spectrum, this 1-bit DACs will cause perhaps some trouble. And of course, I know that you know the answer, but yeah, it's a good discussion. So they will cause some out-of-band radiations due to the high nonlinearity. You have a signal that is infinitely steep. So it will definitely cause some out-of-band interference if you don't have proper filters, ideal filters. Now, my, let's say, workaround to this problem is that when you go to high frequencies, you have large bandwidth, so you don't need to like put signals very close to each other. So you might overcome that. But of course, that's something that you absolutely need to take into account.
Okay, I counted 2 questions, so we will move on. Thank you.
Thank you.
Okay, you can use that. So the next speaker, the last speaker, but not the least, Tommy Svensson from Chalmers, University of Technology, Sweden. And Tommy will be talking about our favorite topic, distributed MIMO, and sometimes was called also as a comp, and multi-TRP, in different G jargons. So let's see what will be the 6G jargon term. Is it the D-MIMO?
I think so, D-MIMO systems.
All right, okay.
Okay, thank you. Thank you for inviting me and thank you for staying. Let's see if we manage to finish by 5. I will try as much as I can, but maybe I need until 5 past. I want to do a quick overview of where I think we are going towards 6G, a quick recap of comp to D-MIMO, and a recap of the key results we did in XX on D-MIMO, and some highlights on research going on at Chalmers, and then an overview of what's going on in D-MIMO in the HexX2 project and some take-home messages. So this will be a more broader than deep presentation. So in 4G, we enable the mobile internet with rich multimedia. We enable densification in different ways, but also both a centimeter wave, a millimeter wave spectrum. We enable the massive Internet of Things connectivity and robustness and low latency. And in 6G, driven by the HexX visions and work, we try to be a robust pillar for the society needs. So digital and human physical parts of our world should be converged, and we should have trustworthiness, sustainability, and digital inclusion, and to try to address the challenges we have. So there are new performance metrics coming up. We also, from tech perspective, convergence of sensing, as already been highlighted today, and computing, so on. Charles been very active in the EU projects, and currently in my team, we're active in HexX2, Robust 6G, and EcoENet. We wrote a paper some time back in the 6G flagship on what are the key enablers for 6G. And I just want to quickly go through the technical enablers we looked at there, and I think all are active. It's massive MIMO, it is RISs or network control repeaters. It's a D-MIMO in the cell-free thinking sense. It is integrating mobility and fast resource allocation. Vertical convergence, especially now with LEO satellite systems, heterogeneous backhauling, integrated access backhaul, where we use the same frequency bands in a more or less tight way, like IIB, and then combining with sensing, localization, information. And everything here, from my perspective, is antennas, and it is a way to densify. And we try to integrate its convergence and integration. So the story from comp to D-MIMO, in 4G times we looked into, we had our base stations, and we didn't want to add more sites. Potentially we could add a relay node or distribute antennas, adjusted antennas, and then have a fiber there, or tight cooperation between existing base station sites. We needed to give up that. Somehow in 5G we realized we need to densify. So can we do it with smaller nodes, so do heterogeneous networking? And if so, can we enable self-backhauling if we use higher spectrum, millimeter wave particularly? Coming from the massive MIMO community, people start to look, okay, if I have so many antennas, can I achieve channel hardening by distributing antennas and do very user-centric grouping of the antenna resources? So, and then in 60 times now with Markku in the lead and others on what other kind of antenna systems can we have that are can be scalable. So RISs and network control repeaters. Looking back, the purpose of corporate communications were to enable coordinated scheduling and/or beamforming to avoid unnecessary interference that we actually could avoid. And that is a more lightweight way to coordinate. The more advanced way is that we do it not only in the control plane, but also in the user plane. So we do joint transmission of the data, or we do joint reception and joint detection in the network. The benefit of D-MIMO in the sense of comp in the centimeter wave world was and is to enable more smooth capacity in the area, because where interference is limited. And that we cannot go away from, because we have sparse spectrum access at the lower bands. And this we got really bad when we started, for example, reuse one systems. So by taking away some of the resources and use them for coordination, we could make it more equal, and add in some relay nodes or smaller base stations in HetNet's concept. We could try to equalize the spatial area fairness. But that trick is not so easy in millimeter wave because the propagation and the coverage is so highly varying, so detailed depending on the environment, the propagation environment. So that's not one size fits all, we think. In the HEXX project, we looked into different D-MIMO approaches. The general theme is that the potential benefits with D-MIMO is to mitigate unreliable links due to shadow blocking, thanks to macrodiversity, and also enabling further densification access points for increased and consistent air capacity, and to achieve sufficient link margin, despite we have an output power limitation, especially if you have small base stations we put mounted for lower down, so they get the peak power limitations similar to user terminals. And in that case, we can allow for low in the RP and still get enough sufficient transmit power and receive power. So we looked into homogeneous cell-free approaches. We looked into different kind of cooperation schemes. We looked into different kind of way to generalize this distribution via different structure, like these are the Ericsson radio weaves or radio stripes and weaves, where the distribution chain and power distribution is integrated and it's easy deployment. And that works in small scale deployments. Whereas in more large scale deployments, integrating access and backhaul approaches has promise. And also have resilience or reliability and macrodiversity in the backhaul. So mesh wireless backhauling approaches. So we simply saw here then that there's not one size fits all. That depends on the functional complexity that we can allow on the deployment cost, what kind of technique that are feasible here. And we did some performance analysis of these techniques. For example, it was more on concept on having analog radio fiber with wavelength division multiplexing, an analog, so centralized analog pre-coding, and then looking to distributed pre-coding, where we distribute in different ways and then different degrees. And we saw that it matters depending on the carrier frequency, what is good and bad here. We looked into different kind of cooperative pre-coding schemes, and then depending on the metric, is particular here, we looked into energy efficiency. And we saw that actually hybrid pre-coding seems to be better than fully digital because we save on the operational hardware energy. We looked into this also combining wireless backhauling and fiber backhauling, and what would it take to avoid fibers or have a subset of the backhauling to be wireless and a subset to be fiber. How much do we need to over provision the wireless backhauling, depending on densities and scenarios. So just to summarize here, that there are many degrees of freedom in the radio architectures, and this is something we think we need to reflect in the system concept and towards standards, that are not one size fits all. So we have different fronthaul options, we have different transmission approaches, we have different processing and deployment approaches, and they have their merits. So we should adaptively use them. And in general, we see that then at the centimeter wave there, we can afford digital approaches, and then maybe can be more distributed because we can afford computing out in the access points. Whereas at the higher bands, we need access points to be very, very cost efficient. And on the other hand, I don't need to be so spectral efficient because we have access to enough of spectrum. But this has impact also on the architecture then. So we need to enable this kind of heterogeneity, so extensibility and flexibility and scalability, and resilience and availability. But one important thing is here also separation of concerns, mean that we should split the control and the user plane, so we enable this heterogeneity. I will not put time on RISs because that Markku talk about in a super solid way. I just want to highlight the potential given they are big enough. And we have done work on different ways here, but I want to highlight them in the context of what I talked about the last Monday in the snow on how can we enable densification by context information. And that information can be statistical channel knowledge or using location accumulate channel knowledge, using sensing information by other systems, resources that are used for communications, or intentions such as moving directions, appellate communication buffer and flow status, and in general situation awareness. Couple of examples where we have used multiple base stations we know the user intentions, we know the communication needs, and then we know the timings, so also where the blockers are and going. So when should we communicate to maximize the throughput and minimize outage? We also compare that with using RISs instead. Another example is where we avoid EMF exposure by explicit knowing where the users are or integrated sensing the appearance of those users by integrated radar sensing, and then optimize the beamforming using the degrees of freedom we have for the direct beam and via an RIS. Lately, we have submitted a paper where we looked into the opportunities for integrating communication localization and sensing in 6G MIMO networks. And we also we did a complete analysis on if we deploy indoor outdoor high or low bands, and then the D-MIMO options we have. So when are the requirements so similar and when are they different for the purpose of communication sensing? So I will not go through the table. I will just show that there are examples here where both options are feasible and possible, and there's certain cases for localization versus sensing versus communications where requirements are quite different, and the possibilities to implement it in D-MIMO are different. So here I think that this can trigger a lot of further research. Another scenario, we looked into sustainable design, and this is an example situation awareness, where we know that there are natural hazards and how can we do a resilient design. So that's what we work on also. This is part of situation awareness. And we are interested to see, can we capture and track all this information we have in a digital twin that are tailor-made for the communication needs. So that is what we are working at Chalmers, and we are very interested in collaboration there. That's an open platform, digital twin city center platform. So I will use started quarter two. I will use 2 minutes, I think, to summarize in 3 slides the ongoing work in HEXAX2 in this domain. So they're working on coherent joint transmission, on non-coherent joint transmission, on decentralized transmission, on adding RIS in the wireless backhauling approaches, and this under different performance metrics, ranging from the scope we have set up for 6G. And they work on multi-antenna caching, on scalable antenna selection, where we are using context information, on EMF constrained distributed transmission schemes, and on distributed massive MIMO for MTC. And finally, the final slide on RIS-assisted transmission, control procedures for external RIS in Russell environments. There are different kind of signal analysis here, 2D, 3D geometries. And Chalmers was also looking into adding RIS in the access part of D-MIMO to see can we blend those in a clever way, because RIS we maybe can have more nodes, but on the other hand, we have some uncontrolled interference. So how can we jointly optimize this? They also work on control procedures for personal RIS and learning RIS and REM. So my take-home messages with this long story is that the scalable and adaptive D-MIMO systems have strong potential. I think we need it because we have so many use cases, so many deployment scenarios and these constraints. But the D-MIMO in general has benefit both at low and high bands, but for different purposes. Context-aided communications aims to enable dense and reliable communication with reasonable overhead, and I think there quite much work we can do there, because we cannot measure and adapt explicitly on everything. We need to learn this on the fly and have models to do the selective decisions on what options we should go for. Sensing-based communication seems very promising here, and there are some interesting research to be done here, integration ISAC in D-MIMO. And in general, of digital twinning might be used for static a priori context information.
Thanks, Tommy. Very efficient. Questions from the audience?
Thank you. Could you go back to your take-home messages?
Which slide?
The last slide.
Previous one.
Yes.
Take-home messages.
Yeah.
Yes.
Okay.
Yes. Yeah, could you comment a little bit on this? Sorry. Yeah, the sensing-based and this ISAC integration. So you are looking at various types of like sensing mechanisms. Can you elaborate on that?
Yeah. So in the context of D-MIMO, we simply wanted to see, okay, if we now want to do distributed sensing using D-MIMO access points, what similarities or differences are there, and what are the differences in the feasibility for implementing? Because we need to motivate the access point. We can't deploy dedicated nodes. Well, we can, but the more we can reuse them for both purposes, the better. But then we also need to understand the similarities and differences in the requirements for sensing localization and for communications. So that is the initial work we did in this magazine paper that is on archive now. It's under review. So
isn't it similar to multistatic sensing?
Exactly. So yeah, so bistatic and multistatic. I mean, in a D-MIMO framework, distributed access points, you can do either monostatic to one, right? But you can do a selection which access point to use, or you can do it multistatic, where you send a sensing signal from one access point and receive it from at another one.
All right. I think okay, maybe one quick questions. Is there another one? We have time? No.
Yeah, I'll try to be quick. Sorry, thank you for the presentation. At the time of Artist 4G and COMP, as you previously showed, one of the limitations we had was the need for a perfect, or at least a very good backhaul between the RF unit and the place where we do the centralization. And in practical, it turns to limit COMP to co-located site, because here it was easy to get this perfect backhaul. What do you think made the situation different now?
Well, the basic technical problem is still there, and the question is, are the incentives? So we think that maybe non-coherent approaches make sense in the upper bands, whereas in the lower bands, maybe we still need to motivate to implement a good sync and implement this overhead. But we also densify the networks in general, meaning that the cooperation areas might be smaller. So that maybe can lower the cost as well. On the other hand, also more dark fiber available nowadays compared to back then. So there might be more opportunities, but this combination of the complexity and how much cost we are ready to take.
Okay, and you don't see any possibility to do some kind of inbound backhauling? Sorry. To rely on the radio access to also assume the backhaul of the radio unit, some kind of in-band backhauling?
Exactly. We at the millimeter wave bands, definitely, because there we have the wide system bandwidth, we can reuse it for self-backhauling. And those IDs didn't take off in the lower bands because there we need everything for access.
Okay, due to interest of time, I think we need to start wrapping up, and let's thank the speaker once again.
Yep.
And it's the end of the last session of the event, and we have Alex to give some concluding remarks.
Thanks very much. Now, who's been having a good time so far? Yay, excellent. Some replies at this stage of the day. That's brilliant. Well, I'd like to say thank you all very much for this. I know we've covered a huge amount of ground over the last 3 days, everything from indoors to the sky and everything in between. So thanks very much for that. If you haven't been able to keep track of everything, or if you've missed some sessions, once again, we will be putting everything onto YouTube, and that should be available next week. We'll send you an email when that's up. So you've got that. One thing that really struck me is that if we look across the sessions, then we can draw lines straight from, let's say, Italo's 1-bit MIMO through to sustainability issues, to spectrum, to national resilience, business cases. Unlike anything I've ever seen before, it feels like the telecoms ecosystem and its concerns are all very intimately interconnected. And so as a result, we're coming to the end of a very academic day, and I'm going to give you 3 pieces of homework. So the first one is, if you've enjoyed this, either in person or online, please do consider visiting 6gworld.com. If you like what you see there, we're going to try and carry on these kinds of conversations and issues across the year. Maybe you'd like to sign up for our newsletter every 2 weeks. The second piece is to please join me in thanking both the hosts nationally, that's Business Finland, 6G Flagship and 6G Finland, and the international partners as well. So Atzeni, the University of Surrey and InterDigital, as well as our sponsors, Huawei, Nokia, Keysight, Rohde & Schwarz, and Virginia Diodes, but most of all our speakers. And more than that, I think you should all give yourselves a great big pat on the back as well for making it through all of this. So that's the third piece of homework for this. And having said that, it's been an absolute pleasure to meet you all this week. Thanks ever so much for coming. Have a great trip back home, and I'll hope to see you all again in September when we do 6G Symposium next in Washington, DC. Thank you.